US Physics Olympiad, year 2016, F equal MA. First round. For this round there were 25 problems for 75 minutes. All solutions for these problems you can find in the reference below this video in the description. Problem 1. A car drives counterclockwise around a flat circular curve at constant speed, so that the left front wheel faces out a circular path of radius r equal 9.6 meters. If the width of the car is 1.74 meters, what is the ratio of the angular velocity about its axle of the left front wheel to that of the right front wheel of the car as it moves through the curve? Assume the wheels roll without slipping. Solution. Suppose that car is moving with a constant angular speed, big omega. In that case, speed of left wheel and right wheel will be omega r for left wheel and omega multiplied by r plus d, where d is width of this car. And now we can write what is the angular speed for both wheels. If small r is a radius of wheel, we have this relation for omega for left wheel and omega for right wheel. Now we can just divide omega L over omega R. That will be R over R plus D, which is 0.847. That's answer E. Problem number 2. A 3 centimeters thick layer of oil with density ρ0 equal 800 kg per cubic meter is floating above water that has density ρw equal 1000 kg per cubic meter. A solid cylinder is floating so that 1/3 is in the water, 1/3 is in the oil, and 1/3 is in the air. Additional oil is added until the cylinder is floating only in oil. What fraction of the cylinder is in the oil? Solution. First, we can write the equation for the floating cylinder. So we have mass of cylinder, which is volume of cylinder multiplied by rho of cylinder. That's equal 1/3 volume of cylinder submerged under water multiplied by rho water plus 1/3 volume submerged in oil multiplied by rho oil. And from here we can find that rho cylinder equal 1/3 rho water plus rho oil, which is equal 600 kilograms per cubic meter. And after that we can write equation for floating cylinder. That will be volume of cylinder multiplied by rho cylinder equal volume of submerged part of cylinder multiplied by rho oil. Now we have V submerged over total V equal rho of cylinder over rho of oil, which is 3/4. That's answer B. Problem number 3. An introductory physics student, elated by a first semester grade, celebrates by dropping a textbook from a balcony into a deep layer of soft snow which is 3 meters below. Upon hitting the snow, the book sinks further 1 meter into it before coming to a stop. The mass of the book is 5 kilograms. Assuming a constant retarding force, what is the force from the snow on the book? Solution. Here we can use a work energy theorem. It means that total potential energy of book is heated by force from snow, which is give us equation mg multiplied by height 3 meters plus distance 1 meter equal force multiplied by distance 1 meter. From here we can find that force equal 200 newtons, which is answer E. Problem number 4. Small bit slides from rest along a wire that is shaped like a vertical uniform helix spring. Which graph below shows the magnitude of the acceleration A as a function of time? Solution. Tangential acceleration equal g multiplied by sine theta, where theta is the angle of inclination for this helix, and also moving by circle, and it has a centripetal acceleration which equal to v square over r, which is a tangential square over r multiplied by t square, and finally total acceleration equal this square root, which is this one. And if we look for graphs, the best way is graph D, which is equal to some kind of constant for 0 time, and going like parabola as asymptotic. So that's the only case, D. US Physics Olympiad, year 2016. F equal MA, first round. Problems 5 and 6. The following information applies to questions 5 and 6. Consider a particle in a box where the force of gravity is down as shown in the figure. The particle has an initial velocity as shown, and the box has a constant acceleration to the right. Problem 5. In the frame of the box, which of the following is a possible path followed by the particle? Solution for problem 5. If box is moving with a constant acceleration a to the right, inside the box, in the frame of reference of the box, we have a fictional acceleration a to the left, and total acceleration will be this one, g prime, which is going down and to the left. In this case, we have motion by parabolic trajectory with the vertex oriented on the top, slightly right and up. Here we have E and D. There are parabolas, but vertex going to top, so it means that total acceleration going down. A is not parabola, and B is a parabola oriented horizontally, which is no good, and only C parabola looks like correct one. So that's the correct answer, C, for problem number 5. Problem number 6. If the magnitude of the acceleration of the box is chosen correctly, the launched particle will follow a path that returns to the point that it was launched. In the frame of the box, which path is followed by the particle? Solution for problem 6. As we mentioned in the previous problem, the effective acceleration of free fall will be g prime, and in any case the trajectory will be either parabola or straight line. If we have g prime is going directly anti-parallel to v initial, we have motion by vertical line frame reference of this box, and the correct answer is A, because other paths, they are not parabolas and not straight lines. That was a solution for problem number 6. Problem number 7. A mass on a frictionless table is attached to the midpoint of an originally unstretched spring fixed at the ends. If the mass is displaced a distance a parallel to the table surface but perpendicular to the spring, it exhibits oscillations. The period t of the oscillation behave like these answers. So we need to find what is correct answer. Solution for problem 7. For big displacement, our potential behave quadratic to displacement. It means that for big amplitude, period approaches a constant fixed value. But for small displacements, we can estimate what is the potential. If this is the picture, we can count potential like this, and approximately for small x, it behaves like x power 4. And power 4, it means that for very small amplitudes, we have a very long period going to infinity when x going to 0. It means that only answer C is correct, that the period decrease as a increase and approaching fixed value when x is going to big numbers, and other answers are not correct. Problem number 8. Kepler's laws state that, first law, the orbits of planets are elliptical with one focus at the Sun. Second law, a line connecting the Sun and the planet sweeps out equal areas in equal times. And the third law, the square period of the planet's orbit is proportional to the cube of its semi-major axis. Which of these laws would remain true if the force of gravity were proportional to 1 over r cubed rather than 1 over r squared? Solution for problem 8. Only second law is connected to the central forces, and the other laws, they are not connected to any other forces except back proportional to r squared. This is why only answer B is correct. This is the answer for problem 8. Problem number 9. A small bead is placed on the top of a frictionless glass sphere of diameter d as shown. The bead is given a slight push and starts sliding down along the sphere. Find the speed v of the bead at the point at which the bead leaves the sphere. Solution for problem 9. First, let's draw the free body diagram. When bead moves by angle theta, we have two forces acting on it. That's normal force and the force of gravity mg. And we can find what is the force in n direction acting on this bead. Because this bead is moving by circular motion, we have normal acceleration equal v squared over r. And that's equal to net force from normal force and mg. We have mv square over r equal mg cosine theta, which is a projection of mg on this direction, minus normal force. And the condition for bead to leave this sphere is when normal force equals 0. And now mv square over r equal mg cosine theta, m is cancelled, and v square equal r g cosine theta. So we have to find what is the relation between cosine theta and v square. This we can find from energy conservation, because the difference in potential energy equal to kinetic energy. 1/2 mv square equal mgr multiplied by 1 minus cosine theta. This is our energy conservation. Now we can find what is cosine theta by equalizing this v square and this v square. That will be this equation, and cosine theta equal 2 over 3. It means that v square equal 2 over 3 gr. And finally v equal square root from gd over 3, which is answer E. That was solution for problem number 9. Problem number 10. Two blocks are suspended by two massless elastic strings to the ceiling as shown in the figure. The masses of the upper and lower block are m1 equal 2 kg and m2 equal 4 kg respectively. If the upper string is suddenly cut just above the top block, what are the accelerations of the two blocks at the moment when the top block begins to fall? Solution for problem number 10. First, let's write the free-body diagram. If we have tension T1 in upper string and tension T2 in lower string, and we have force of gravity on M1, it's M1G, and on M2, M2G, so we have two equations for static equilibrium. We have T1 equal M1G plus T2, and the T2 equal M2G, and T1 equal 60 newtons and T2 equal 40 newtons. When we cut upper string, immediately after that T2 is still 40 newtons, and we have other equations. So M1 A1 equal M1G plus T2, and M2 A2 equal Mg minus T2. We see that M2G equal T2, so that's equal 0. M1 A1 equal 60 newtons, and M2 A2 equal 0. From here we can find that A1 equal 30 meters per second and A2 equal 0. That's the answer D, which is correct. That was a solution for problem number 10. Problem number 11. The power output from a certain experimental car designed to be shaped like a cube is proportional to the mass m of the car. The force of air friction on the car is proportional to AV square, where V is the speed of the car and A the cross-sectional area. On a level surface, the car has the maximum speed V maximum. Assuming that all versions of this design have the same density, then which of the following is true? To which expression Vmax proportional? First, we have a power equal force multiplied by velocity, and power proportional to mass, and force proportional to AV square. So we can write down mass proportional to a v cube, and because cross-sectional area proportional to mass power 2/3, we have this proportionality, and from here we have mass power 1/3 proportional to v cube, and v proportional to m power 1/9, which is answer A. That was solution for problem number 11. US Physics Olympiad, year 2016. F equal MA, first round. Solutions for all problems you can find in the reference of the description below this video. If you are not subscribed yet, please do this. Problem number 12. Block floats partially submerged in a container of liquid. When the entire container is accelerated upward, which of the following happens? Assume that both the liquid and the block are incompressible. Solution for problem number 12. According to Archimedes' principle, we have weight of this block, rho of block multiplied by volume multiplied by g, that's equal to weight of displaced liquid, which is rho liquid multiplied by displaced volume and VL and multiplied by g. When we have acceleration upward in this system of container, we have additional frictional force, which is changing acceleration of free fall proportionally. So it means that we have equation looks like this, and from this we can see that VL is not changing. So it means that the correct answer is C. The block does not ascend or descend in the liquid. That was the answer for problem 12. Problem number 13, not 12. An object of mass m1 initially moving at a speed v0 collides with an originally stationary object of mass m2 equal alpha m1, where alpha less than 1. The collision could be completely elastic, completely inelastic, or partially inelastic. After the collision, the two blocks move at speed v1 and v2. Assume that the collision is one-dimensional and that object 1 cannot pass through object 2. After the collision, the speed ratio r2 equal v2 over v0 of object 2 is bounded by next inequalities. Solution for problem number 13. In case of absolutely elastic collision, we have solution for R1 and R2 looks like this. These results we can find using energy conservation and momentum conservation for this collision. And the best way to solve this problem is to use frame of reference of center of mass. And I suppose that you know this result. In case of alpha less than 1, we have first object is moving after collision in the same direction as rebounding object 2. And object 2 has maximum possible speed after this collision. If we have absolutely inelastic collision, they are slip together after collision, and object 2 has a minimum possible speed, which is equal to which we can find from this relation. And now result will be E, correct answer, because in case of absolutely inelastic collision we have minimum possible speed, and in case of absolutely elastic collision we have maximum possible speed of the second object. So correct answer is E. Problems number 14 and 15. The following information applies to questions 14 and 15. A uniform rod of length L lies on a frictionless horizontal surface. One end of the rod is attached to a pivot. An unstretched spring of length L much greater than small l lies on the surface perpendicular to the rod. One end of the spring is attached to the movable end of the rod, and the other end is attached to a fixed post. When the rod is rotated slightly about the pivot, it oscillates at frequency f. Problem number 14. The spring attachment is moved to the midpoint of the rod, and the post is moved so that the spring remains unstretched and perpendicular to the rod. The system is again set into small oscillations. What is the new frequency of the oscillation? Solution for problem number 14. Suppose that the moment of inertia of this rod around the pivot is I, and we made a displacement of right end by small angle theta. In that case, displacement of this spring will be r theta, and the force from the spring will be negative kr theta. It means that now we can write equations for motion of this rod, for rotation of this rod. Let's equal I alpha, where alpha is angular acceleration, multiplied by force and multiplied by distance from pivot to the spring end. And now we can insert F here and write the equation. This equation I alpha equal negative kr squared theta is a regular equation for harmonic oscillation, because alpha is angular acceleration and theta is a corresponding angle. From here we can find what is frequency. Frequency equal to this expression, and you see that it's proportional to distance from pivot to the spring end. It means that for the problem number 14 we reduce this distance twice. It means that frequency will reduce twice, and that the correct answer is A for problem number 14. That's the answer. Problem number 15. The spring attachment is moved back to the end of the rod. The post is moved so that it is in line with the rod and the pivot, and the spring is unstretched. The post is then moved away from the pivot by an additional amount L. What is the new frequency of oscillation? Solution for problem number 15. Now, because we have initial extension of this spring is L, we can assume that this force from spring will be constant, because enlargement is very small compared to length of this L. So force equal just to KL, and the lever arm equal to L theta, because small h much less than big L. And finally we have this equation for rotational motion. I alpha equal negative KL squared theta. But this is the same equation as in the original case, because R equal L. It means that in this case we have the same frequency as in the original example. So correct answer is C. That was solution for problem number 15. Problem number 16. A ball rolls from the back of a large truck traveling 10 meters per second to the right. The ball is traveling horizontally at 8 meters per second to the left relative to an observer in the track. The ball lands on the roadway 1.25 meters below its starting level. How far behind the track does it land? Solution for problem number 16. First, we can write the equation for fall of this ball. Height h equal 1/2 gt squared. And from here we can find what is time to fall down. That will be square root from 2h over g, or half second. And now we can find what is the total distance relative to track. That will be vt, where v is speed of ball relative to track, and time t is half second. Answer is 4 meters, which is answer C. That was solution for problem number 16. Problem number 17. As shown in the figure, a ping pong ball with a mass m, with the initial horizontal velocity v and the angular velocity omega, comes into contact with the ground. Friction is not negligible, so both the velocity and the angular velocity of the ping pong ball changes. What is the critical velocity Vc such that the ping pong will stop and remain stopped? Treat the ping pong ball as a hollow sphere. Solution for problem number 17. Here we can use angular momentum conservation. If we take axis of rotation right in a table perpendicular to this picture, we can count what is the total torque of all forces around this axis. We have gravity force and we have normal force, which cancel each other. And also we have force of friction, which is going through this axis of rotation. So it means that the total torque acting on this ball is 0. It means that total angular momentum around such axis is 0. And let's write this equation for total angular momentum. If we have a solid body which is moving around axis of rotation, total angular momentum equal mass multiplied by velocity of this body and multiplied by distance from the center of mass to this axis of rotation. And we need to add here angular momentum around the center of mass. In our case, because omega is counterclockwise, that will be negative, and that will be negative I omega, and the total equals 0, because finally it will stop. From this equation we can count. Because I equal 2/3 mr square, we can insert this I in this equation and finally find that velocity equal 2/3 r omega, which is answer A. That was a solution for problem number 17. Problem number 18. A spinning object begins from rest and accelerates to an angular velocity of omega equal pi over 15 radians per second, with an angular acceleration of alpha equal pi over 75 radians per second square. It remains spinning at that constant angular velocity and then stops with an angular acceleration of the same magnitude as it previously accelerated. The object made a total of 3 complete rotations during the entire motion. How much time did the motion take? Solution for problem 18. First of all, we can find what is time for acceleration and deceleration. This we can count from formula omega equal alpha t1. So we have t1 equal omega over alpha, which is 5 seconds. After that, we can count what is total rotation for this object. Total angle theta, which is 6 pi in radians. That's equal twice distance with acceleration, which is alpha t1 square, plus omega t2, where t2 is time for constant angular velocity. So from here we can find that omega t2 equals 6 pi minus 1/3 pi, which is 17 over 3 pi. And from here we can find that t2 equals 85 seconds. And total time t equal twice t1 plus t2, which is 95 seconds. That's the answer E. This is solution for problem number 18. Problem number 19. A semicircular wire of radius r is oriented vertically. A small bead is released from rest at the top of the wire. It slides without friction under the influence of gravity to the bottom, where it then lifts the wire horizontally and falls a distance h to the ground. The bead lands a horizontal distance d away from where it was launched. Which of the following is a correct graph of RH against d square? Solution for problem number 19. First, we can find what is the speed of this bead when it leaves this wire. From energy conservation, we have v square equal 4gr. Now we know what is speed, and we can count what is total time to travel. For that, we can use formula h equal 1/2 gt square. From here we can find that time equal square root from 2h over g. It means that total distance equal vt or square root from 8rh. And finally we have rh equal 1 over 8 d square. This is the graph D. That's a straight line with the origin and a 0 point. D is correct answer. That's the answer for problem 19. Problem number 20. A uniform solid right prism whose cross-section is an isosceles right triangle with a height h and the width w equal to h is placed on an incline that has a variable angle with the horizontal theta. What is the minimum coefficient of static friction so that the prism topples before it begins sliding as theta is slowly increased from 0? Solution for problem 20. To topple this prism, we need to draw a better picture. On this picture we can see that if center of mass of this prism going through the corner of this prism, that will be critical angle to topple this prism. From geometry we can say that this center of mass stay on height 1/3 h from base. So it means that tangent of this angle between this vertical and this base of prism must be equal 1/3. It means that tangent theta equal 3. But we have critical angle when body start to slide. Tangent theta equal mu, coefficient of static friction. So this is why we have tangent theta equal mu equal 3. That's the answer E. This was the solution for problem number 20. Problems number 21 and 22. The following information applies to questions 21 and 22. A small ball of mass 3m is at rest on the ground. A second small ball of mass m is positioned above the ground by a vertical massless rod of length L that is also attached to the ball on the ground. The original orientation of the rod is directly vertical, and the top ball is given a small horizontal nudge. There is no friction. Assume that everything happens in a single play. Problem number 21. Determine the horizontal displacement x of the second ball just before it hits the ground. Solution for problem number 21. Here we don't have friction. It means that center of mass not moving horizontally, and it means that the distance of heavy ball is 3 times less than distance of a small ball, and the total distance between these balls is L. So it means that distance of big ball from initial position of this rod is 1/4 of L, and the distance of a small ball is 3/4 of L. And this is the answer A. That's the solution for problem number 21. Problem number 22. Determine the speed v of the second originally top ball just before it hits the ground. When a small ball reaching the ground, it has only vertical speed, because horizontally this rod not moving. The horizontal momentum is 0. So it means that total potential energy of this system, which is mgl, going to kinetic energy of this small ball. The big ball is not moving at all. So we have this energy transform equation, and from here we can find that speed v equal square root from 2gl. This is the answer A, and this is the solution for problem number 22. US Physics Olympiad, year 2016. F equal MA, first round. Problem number 23. A uniform thin circular rubber band of mass big M and the spring constant K has an original radius R. Now it is tossed into the air. Assume it remains circular when stabilized in air and rotates at angular speed omega about its center uniformly. Which of the following gives the new radius of the rubber band? Problem number 24. The moment of inertia of a uniform equilateral triangle with mass M and side length A about an axis through one of its sides and parallel to that side is 1/8 ma square. What is the moment of inertia of a uniform regular hexagon of mass M and side length A about an axis through two opposite vertices? Problem number 25. 3 students make measurements of the length of a 1.5 meter rod. Each student reports an uncertainty estimate representing an independent random error applicable to the measurement. Alice. A single measurement using a 2 meter long tape measure to within ±2 millimeters. Bob. 2 measurements using a wooden meter stick, each to within ±2 millimeters, which he adds together. Christina. 2 measurements using a machinist's meter ruler, each to within ±1 millimeter, which she adds together. The student's teacher prefers measurements that are likely to have less error. Which is the correct order of preference?